When a heavy vehicle hits a sudden incline at high speed, the suspension is forced to absorb a massive spike in kinetic energy. If the mechanical system cannot process that energy fast enough, the suspension bottoms out and the hardware shatters. Engineers cannot afford to find these breaking points by repeatedly crashing physical prototypes. Instead, they translate the physical mass, springs, and dampers into mathematical models to simulate the failure before the first piece of steel is ever cut. To test a mathematical model, you have to hit it with a simulated force. Since the exact real-world disturbances are unpredictable, engineers rely on a specific set of standardized mathematical input signals to provoke a response. This grid displays 4 primary test signals used in control engineering. The unit step, highlighted here, represents an instantaneous change in a system's target, testing how it reacts when suddenly commanded to move from 0 to 1. The unit ramp simulates a target moving away at constant velocity, measuring the system's ability to track a moving objective. The impulse input represents a massive shock of energy delivered in a microscopic fraction of a second. By calculating exactly how a system responds to these abstract signals, engineers map the absolute physical boundaries of the machine. The simplest dynamic models are first-order systems. These are governed by a single energy-storing element. A common example is a thermal heating unit, where heat is continuously stored and gradually released. The performance of a first-order system is defined by a single parameter, known as the time constant, represented by the Greek letter tau. Tau dictates the physical speed of the system's response. This chart compares 2 first-order systems reacting to a unit step command. The red line, with a time constant of 50, climbs steeply toward the target amplitude of 1. The blue line's time constant is doubled to 100, so its response is sluggish. Mathematically, a system reaches 63.2% of its target exactly when elapsed time equals its time constant. Hitting a stationary target is straightforward. But the physics change when the system has to track a continuously moving target, represented by a ramp input. Here, the upper diagonal line is the moving target. The lower line is the first-order system trying to catch it, falling permanently behind into a parallel trajectory. This vertical gap is the steady-state error. In a first-order system tracking a ramp input, this physical tracking error is mathematically equal to the system's time constant, tau. Engineering the time constant to be as small as possible is the only way to maximize physical speed and minimize tracking error. When you add a second energy-storing element to a machine, like a mass interacting with a spring, you create a second-order system. This introduces new dynamics. This graph compares a first-order to a second-order response returning to equilibrium. The red curve exhibits a smooth, predictable exponential decay to 0. The blue line shows the second-order system violently overshooting. The mass and spring exchange kinetic and potential energy, forcing the output to oscillate wildly above and below 0 before finally settling. The rate at which this chaotic kinetic energy is absorbed and dissipated is governed by a parameter called the damping ratio, or zeta. This graph shows a system where the damping ratio is exactly 0. With 0 damping, the physical energy has nowhere to go. The system will oscillate infinitely. To prevent this, engineers target an underdamped state, setting the damping ratio between 0 and 1. This balances a fast initial movement with enough resistance to eventually absorb the excess energy. Engineers measure this underdamped curve using 5 transient performance specifications. Delay time and rise time measure the initial burst, calculating how long it takes to launch toward the target. Peak time and maximum overshoot measure the extreme limit of the first swing, warning engineers of the maximum physical stress the hardware will endure. Finally, settling time is the moment the kinetic energy is exhausted enough that the system remains stable within a strict 2% margin of the final goal. Tuning the damping ratio requires a strict engineering compromise. You must trade off how rapidly you want the machine to move against the amount of violent overshoot the hardware can physically survive. Beyond speed and accuracy lies the absolute limit of system performance, bounded input, bounded output stability, or BIBO. The rule of BIBO is strict. A finite, controlled input must always result in a finite, controlled output. If the internal energy multiplies and the output grows infinitely, the machine destroys itself. To predict stability, engineers map differential equations onto a 2-dimensional coordinate system called the S-plane.
If mathematical roots land in the left half-plane, the system dissipates energy and remains stable, but the right half-plane represents exponential growth. A single mathematical root crossing into this territory guarantees a catastrophic failure. Engineers can use the Routh-Hurwitz criterion as an algebraic shortcut to detect if any roots exist in this red zone without computing the complex math. However, Routh-Hurwitz is only a static pass or fail test. It does not show how roots move dynamically as engineers adjust the controller gain.
For precise dynamic tracking, we use the root locus method. It calculates the exact physical pathways these roots will take across the S-plane as the controller gain increases. As you push the gain slider higher, you can watch the roots migrate toward the center axis. The exact millisecond they touch it, the machine reaches the threshold of critical instability. If the gain goes any higher, the roots cross into the right half plane. The physical machine begins vibrating uncontrollably until its joints buckle entirely. The root locus mapping allows engineers to visually identify the exact controller gain that will cause a system to tear itself apart, preventing physical disaster purely through applied math. Control engineering transforms abstract equations into the functional tools used to mold physical reality. A system's differential order dictates its intrinsic shape, predetermining whether a machine will yield a smooth exponential curve or a chaotic wave. Manipulating the damping ratio allows humans to securely control the trade-off between mechanical speed and physical overshoot. And spatial maps like the root locus define the absolute boundaries of controller power before an engine is ever turned on. These predictive concepts form the invisible architecture running quietly beneath modern society. This mathematical framework keeps commercial airplanes stable at cruising altitude, ensures power grids remain perfectly balanced, and allows surgical robotics to operate with precision. By mastering these dynamic parameters, engineers stop reacting to physical forces. They dictate them.